Welcome to the Explainer. Today, we're tackling something that usually has people reaching straight for their graphing calculators, polynomials. But you know what? We're ditching the calculators today. We're going to take a totally visual approach and look at how the literal DNA of these equations instantly dictates their physical shape. So how exactly do you graph a monster? Let's treat a massive, intimidating algebraic equation like a crime scene, right? It's really just a set of clues waiting to be deciphered. We're going to play mathematical detective here. By just looking at the underlying structure of an equation, you can actually sketch its shape super efficiently. No heavy lifting required. Okay, first things first, a super quick refresher on our baseline definition. What exactly is a polynomial function? Well, these guys are built strictly on non-negative integer exponents. Take a look at this one. F of x equals 4x to the fifth minus 3x squared plus 2x minus 5. See? No fractional powers and definitely no variables hiding down in the denominator. Because of this super clean, predictable structure, we know the domain stretches infinitely in both directions. Basically, these graphs just keep going forever.
Here's our quick roadmap to break this all down. 1. Meet the polynomial. 2. The big picture. 3. Finding the anchor points. 4. Cross or bounce. 5. Twists and turns. And finally 6. Putting it all together.
All right, moving right along to section 1. Meet the polynomial, anatomy of an equation. Now, what's really wild here is how identifying just 3 simple elements gives away the entire core identity of our function. First up, we've got the degree, which is literally just the maximum exponent. It tells us the overall power of the polynomial. Next is the leading term. This is the whole chunk of the equation that contains that highest power. Yep, including its coefficient. And finally, we look for the constant term. That's a solitary number just hanging out at the very end with no variable attached. That little guy is absolutely crucial because it tells you exactly where the graph crosses the y-axis. Seriously, just these 3 pieces give us almost the whole shebang.
Section 2. The big picture. Zooming out to space.
Okay, imagine zooming way out. The messy middle of the graph just becomes a blur, and all we care about is where the arrows at the far left and far right are pointing. This illustrates a brilliantly simple binary pattern based on mathematical parity. An even degree? That means the ends match. Think of your standard quadratic parabola. It has an even degree of 2, right? Both ends go up together or they go down together. But an odd degree, like a cubic function with a power of 3, those ends split. They head in completely opposite directions. It starts low and ends high, or vice versa.
Now, let's bring that leading term back in. It's a dominating force that dictates exactly where the graph goes as your x values get infinitely huge. If the number in front of that leading term is positive, the right side of your graph will always, and I mean always, go up towards positive infinity. If that leading coefficient is negative, the right side goes down. So if you just combine this coefficient rule with that odd and even parity we just talked about, boom, you instantly know the starting and ending arrows of your entire graph before you've plotted a single coordinate.
Let's zoom back in a bit for section 3. Finding the anchor points, pinpointing the intercepts.
So, we've mapped the edges of space, but we need our exact coordinates, our x-intercepts. We find these by setting factored pieces of the polynomial equal to 0, which works like magic, thanks to the principle of zero products. Basically, if you multiply a bunch of numbers together and the answer is 0, well, at least one of those numbers has to be 0, right? So, we break our polynomial into smaller chunks and look at each one. A factor of x minus 4, that gives us a root anchoring right at x equals 4. A factor of x plus 1 anchors us at negative 1. And x minus 7 drops an anchor at 7. These are the exact, precise spots where our monster meets the x-axis.
Section 4. Cross or bounce. Reading the local DNA.
All right, we've got our anchors plotted. Now we have to figure out how the graph behaves when it actually hits those specific points. Enter multiplicity. This is essentially a hidden instruction manual embedded right in the exponent of each factored root. Multiplicity is simply defined as the number of times a specific factor repeats. So if you've got an equation with a factor of x plus 3 squared, the multiplicity of that specific root at negative 3 is exactly 2. Now, if you see a factor like x minus 5 just sitting there all by itself with no visible exponent, it actually has an invisible implied exponent of 1. So its multiplicity is 1.
And here's where our binary pattern recognition kicks in perfectly again. Odd means cross, and even means bounce. If the multiplicity of a factor is an odd number, like 1, 3, or 5, the graph slices straight through the x-axis at that point. Why? Because raising a number to an odd power allows the overall mathematical sign to change from positive to negative, or the other way around.
But if that multiplicity is an even number, like 2 or 4, the math forces the output to stay positive no matter what. Because the sign can't change, the graph just comes down, touches the x-axis, and bounces right off, heading back into the same territory it came from.
Section 5. Twists and turns, the rules of the road.
Okay, check out this quote. Polynomials are continuous and smooth curves. They have no breaks, holes, or sharp corners. This is incredibly important to remember. It's what separates a polynomial from something like an absolute value function, which has a really harsh, sharp V-shaped corner. Think of it like driving a car down a winding road. When you graph a polynomial, you never lift your pencil from the paper, and you never, ever draw a jagged point. It is made entirely of graceful, flowing curves.
Because of that smooth, flowing nature, there's actually a strict mathematical speed limit on how curvy the graph can get. The absolute maximum number of turning points a graph can have is simply its degree, represented by the letter n, minus 1. Simple as that. So if you're evaluating a degree 5 polynomial, you know immediately it can turn a maximum of 4 times. A degree 3 polynomial turns at most 2 times. It might turn fewer times for sure, but it can literally never exceed n minus 1. This gives us a brilliant sanity check when we're sketching this all out.
And finally, Section 6, putting it all together, drawing the suspect.
Let's synthesize all of this. By following this strictly logical 4-step framework, you can look at an impossibly intimidating equation and draw it in one smooth motion without breaking a sweat. Step 1. Find your end behavior. Use that leading term to draw your starting and ending arrows way out on the sides. Step 2. Plot your intercepts. Factor it out, use the zero product principle, and drop those anchors directly onto the horizontal axis. Step 3. Check the multiplicity. Figure out ahead of time if you're going to be crossing through or bouncing off each anchor. And Step 4. Just connect the dots. Start at your left arrow, weave through your anchors using smooth, continuous curves that respect your cross or bounce rules, and finally link up with your right arrow.
Now, you absolutely have the tools to cleanly map out real polynomials. But it does kind of leave us with a pretty massive question. If we can deduce all this elegant structure from real roots on our visible number line, what kind of bizarre, beautiful shapes exist when we introduce complex numbers? You know those equations that just float entirely above the axis and never actually touch it? That is a fascinating mystery that really pushes the boundaries of algebra, and it's the perfect puzzle for you to chew on next. Thanks so much for joining me on this explainer, and I'll see you next time.